right? Chapter 3A, we took that test earlier. You guys should have it by the end of the week. Corrections, though, won't be due until next week, which is getting into our final review, etc. So it's something else for you to be reviewing, because that's a good thing to do as you do corrections, etc. But we looked at it as a class, section 3.6, 3.7, and 7.7, 3 sections. And where are we right now? 3.7. And when's that homework due? Tomorrow. So when do we start the last section? Tomorrow. Which makes sense, there's a quiz coming up. A test? No, it's only 3 sections. We're not going to do a test. We'll call it a quest. It's a quiz that counts. Sound good? Okay. We'll have a little baby review for that, etc., because we only reviewed from Chapter 3A last time. We'll review Chapter 3B. So that is coming, just a quick heads up. But have we had any forever cards yet? No, because optimization isn't supposed to be crazy and hard. Optimization is just what kind of problem? Max min. How do you find max's mins? All the stuff that we've been doing since first part of chapter 3. Critical numbers, unless there are, I'm trying to keep reminding you, because the AP is going to have types of problems where you need to remember, unless you have what? Endpoints. And if you have endpoints, we'll be going to a table and testing. But have we had endpoints in all these like real life problems very much? No, because if you have like something, a measurement being 0, then you don't quite have the cone or the triangle or the cylinder or the whatever else we see today. Okay, so optimization, not a big deal. It's a max-min problem, which is all the skills from chapter 3A, kind of. The next section, local linear, talking about it. What do you need to know? Tangent line, an old forever card. But how to use it. A tangent line, an old forever card, but how to use it. And then section 7.7, there is going to be a forever card from L'Hôpital's rule. L'Hôpital's rule, kind of like keep going, or you prime, something to remember. But we'll get there when we get there. All right, cool kids, here we go. Section 3.6, optimization, max-min problems. Only 2 evens for us to really, really, really grade. Number 8. Number 8, the final answer is the 2 numbers. X is square root of, what would that be? 18, aka 3 root 2. And Y is 36. Super awkward, I know, because X is not a pretty number, but it is a right number. Such that the product is a maximum. You had to take your clue, you had to solve for Y, and plug and chug, and then, do you love yourself? Rewrite it first, then take a derivative. Find the critical number. Plus or minus, wait a minute, why didn't we use the negative one as well to test? Positive numbers, so we ignored the negative one. Now they went ahead, now they were snazzy, because they were like, the second derivative is super easy, it's negative 6x. They went ahead and used what test to tell that this is a relative max? What test is this? It's not a sign chart, it's not a before and after, which is hopefully what you did, because that's what we did, and that would have also showed a max. But how does this show a max? The second derivative test says, give me your critical numbers. Not you're poor, you're tired, you're needy. How does that go, Statue of Liberty? Give me your poor. Anybody have that memorized? No one? Anyway, give me you're tired, you're poor, you're... Anyway, done. Give me your critical number. I'll tell you what does this tell me? If it's less than 0, the second derivative is less than 0. Concavity. What's my original function's concavity? Concave down. So if it's down and there's a horizontal tangent, where is it at? Yeah, come on guys, it's a forever. But anyway, second derivative test for relative extrema also tells us it's a max. Guess what? Max. When x is equal to this guy, and how'd they find y? Plug it into your clue. Number 46. I need to zoom in on this one. There's too many words. Oops, that's not what I want. Sorry, zoom in's here. All right, what do we got? Ooh, is this a picture-y one? Is this a brutal picture-y one? Is this the picture-y one that I have in the notes just waiting for us? I don't remember. Was it this one? Ha! It was. Look at me being all ready and prepared. Okay, let me give you a second to see whether or not your answers are right or wrong. And then we'll go talk about the answers. Just see if you're right or wrong. Increasing 0 to 40. Profit is decreasing 40 to 60. Maximum profit is going to be at 40,000 about. And the point of diminishing returns as they described it point where the concavity changes, aka the point of inflection, is about $20,000. Were you right or wrong? See if you're right or wrong. Let's go talk about it real fast. Why is this a funny one? Oh, wait. What did they give you? Okay, it's the name of the graph. What'd they give you? Okay, whew, there you go. Profit of a company. Guys, awkward. So profit of a company. They gave you profit. And what are they asking about? Profit. Oh! This isn't even like that we did the day before, or the homework, or no, the back of the spiral problem that we did before that, where it was a graph of a derivative. This is just the graph of the guy, right? Oh, so where's the profit increasing? Where it's going up? Oh, that's easy, 0 to 40-ish. Oh, where's profit decreasing? Where it's going down, 40 to 60-ish. Well, this was way too easy. They should have said something about the derivative of profit. Oh, well. That's okay, we can do this. Going up 0 to 40, going down 40 to 60. Now it says, estimate the amount of money the company should spend in order to yield a maximum profit. Well, guys, there's the max, right? That's easy. Isn't that something around, what, 3,600? What'd they say, about 4,000? I don't know, a little bit less than that, right? 3,500, 3,600, something like that. That would have been okay. You didn't have to do exactly what they did. Wait a minute. Hold on. Are they asking for the profit? No. So what were you supposed to answer? 40,000. Yeah, good. That's why they said 40,000. So it's not that they were off with this one. That's actually 3,500,000. Oops. They should spend about 40,000 to maximize their profits, according to the projections. And then letter D, you guys have heard that, right? According to the projections. The point of diminishing returns is the point at which the rate of growth of the profit function begins to decline. The rate of growth. Isn't that like a derivative? Rate? Derivative, isn't that like a slope? Don't you want the rate to be positive? Oh. Begins to decline. Where will it begin to decline? Do you guys remember when the derivative is decreasing? What's true about the original graph? F prime decreasing means F double prime is negative, which means F is concave down. F prime decreasing means his derivative, F double prime, is negative, which means F is concave down. So I want to look out for anywhere F is concave down, because wherever F is concave down, what's happening to the rate? It's decreasing. Oh, okay, so look at your graph. When does it become concave down? Here. The rate is growing up until the point of diminishing returns, and then what starts happening? The rate is decreasing. So where would be that point? Well, it's inflection. The point of inflection is going to happen somewhere between 0 and 40. Maybe you guessed 20, if you were guessing. Does that make sense? So they didn't tell you specifically point of inflection, but it is, because where the rate starts decreasing, the concavity changes. Concave up, the rate's increasing. Concave down, the rate's decreasing. So estimate the point of diminishing returns, 20. Does that make sense? 20 as in 20,000, because that's the units. And then you guys had 52 and 54, which we talked about yesterday. I don't think we checked B. Is that the one we didn't check? Somebody had a B. I forget who it was. Somebody had a B. 52A, we already did all this work as far as Pythagorean theorem. Well, they did the nasty way, didn't they, with the right triangle? I think we solved for H, whereas they solved for R. Or was that the other one? Oh, that was 53. Sorry. Oh, we did this one, letter C. Sorry. Is B number 54? Okay, the perimeter one or whatever. So 36 square units, we talked about that one yesterday. Number 54, here he is, the rectangle inside. For letter A, our final answer is 10. Oh, they rationalized, little stinkers. Oh, well, I guess it's all right. They rationalized 10 root 3 over 3, whereas I think we just did 10 over root 3. And then, but hold on. I thought for letter A, didn't they ask for the dimensions? Can you guys check that out real quick? Yeah. They asked for dimensions. Well, that's silly. Who cares about the maximum area? They asked for dimensions. So dimensions were going to be 10 over rad 3, or 10 root 3 over 3, and 50 over 3. And we did that yesterday, I think, because I remember doing like a 75 thirds and then combining the common denominators. So just the dimensions. I don't know why they kept going. I mean, I guess they could, but that wasn't what they were asking for. And then letter B, here's that perimeter one, where you had to end up doing 2 times the length, which was 2 times 2x, and then 2 times the height, which was 2 times y. Plug in your clue, simplify, take a derivative, critical numbers. You end up with x equals plus or minus 1. But like we did yesterday, a positive 1 is the same rectangle as a negative 1. So what would, does it say dimensions again? Little stinkers. So the dimensions, forget about the perimeter, that's not the point. The dimensions are going to be 2 by 24. Is that weird? Careful. X is 1, but remember that's only half the length. Does that make sense? 2x was the full length. So if you're doing the dimension of the rectangle, how long? 2 times 1, 2. And then how high? 24. That's kind of awkward though, right? Huh, a 2 by 24 has the longest perimeter. Go figure. I wouldn't have guessed that. Anyway, has the maximum perimeter. All right, cool kids. With that, what questions do we have on the odds? Nice thing is on the evens, I think those are pretty straightforward because we just talked about that one. This one was a lot like the example in the book, but I'm not pretending like the odds couldn't have gotten hard. You guys were able to check them back of the book. Chat 2. What do we got? 21? 41? 41. Okay, let's go ahead and go to 21 first. You guys be checking out your 21 work because maybe you got it, and if so, be ready to answer those questions because you might answer it in a way that makes sense. Every year, every chapter. Oh, the Norman window. I like this guy. You guys probably hated him. Lo siento. Let me do this. I'm going to go ahead and copy him. I'm going to come over here. Let me go ahead and new page him. And then let me get rid of this. All right, what do you guys see as far as shapes in the Norman window? A square? Almost. Because I'm not sure that x and y are the same. Does that make sense? So I'm going to say rectangle. And then what else do you see? Half circle. Good. I see a rectangle and a half circle too, right? And they even tell you joining a semicircle to the top of an ordinary rectangular window. The dimensions of, okay, hold on. All of this is, isn't this all just kind of like whoop-de-doo, semicircle, rectangle? Okay, it doesn't really mean much besides, okay, geometry. I'm going to think semicircle and rectangle. Then what? What's your primary? Careful, dimensions. Isn't that who we're supposed to be finding? Okay. Maximum area. There's. So A is equal to, oh, it's not. X times Y, but my rectangle. Pi x over 2 squared. Why? R is x over 2. The semicircle is based upon the rectangle, because if you have a semicircle of a different measurement than the rectangle, it's going to be a funny looking window, because then he's going to be shorter or longer. So he has to have the same diameter as x. Half of x is going to be the radius. Anyway, all that to say, that's my primary. Do I have a clue? "16 feet equals perimeter." Okay, I know. You're not going to like this. Perimeter. Is it the actual casing of the window, or is it the around of the shape? Meaning, do I do this plus this plus this plus this plus this? Around. Based on what they said. Just the around. So the around, isn't that going to be 2y plus 1/2 2 pi r? Wait, what's 2 pi r? Why am I using that? Circumference. And do you see that the semicircle is going to have a circumference? But how much of a circumference will that semicircle have? If I'm just going around, I'm just measuring this. So I have half the circumference, and I have most of the 1x, I have 2 y's, and I have 1/2 2 pi. Who's r again? X over 2. What's the purpose of the clue? Does that make sense? Purpose is to get rid of it. So to get y by itself, oh dear. Well, I guess those 2's can cancel. but then I have a 1/2. I'm going to have a bit of a mess, but that's all right. I'm just going to go for it. So I'm going to have 16, take away x, take away the 1/2 pi x, and then divide by 2. Do you guys agree with my math? Just because you were able to do it? Okay. Can I simplify that at all? Do I want to simplify that at all? I guess I could a little bit. Sorry, not equals minus, right? Divide, divide, divide. I guess that's about as good as I can get it. Yeah. Okay. What's all this for the purpose of? Plugging in to be able to derive, right? So can I go ahead and distribute this x, guys? Is that okay? So I'm going to end up with x times 8 minus 1/2 x squared minus 1/4 pi x squared plus, what's this going to be? X squared over 4. 4 times 2 is 8. Do you guys agree with 1/8? That looks right, right? What's the purpose? 8 minus x minus 1/2 pi x plus 1/4 pi x. Oh, hey, I have some like terms. I didn't even notice. That's all right. So what's negative 1/2 plus 1/4? I think that's negative 1/4. Critical numbers. Ew, I don't like, oh well, you got to go for it. I can subtract by a negative. I'll end up with x plus 1/4 pi x positive 8. Subtract the 8, divide by a negative. Do you guys see how I can factor out an x? Oh, and I can divide what's left to the other side. You guys have had time to try this, hence why I'm going a little fast. But I could divide by 1 plus 1 pi. Then we would think of things like domain and like well, it's not possible because I have a window, but I can't go bigger than 16, that's for sure. Well, actually, if I went up here, I bet I could go bigger than something less than, because if that's 0, I have an x there, and I have an x here, over 1 plus 1/2 pi. That's awkward, but it's true. 1/2 8-ish, I guess, maybe, a little bit less than 8, if I was to think logically. So I could do a little psh, psh, psh with a 0, with a 16 over 1 plus 1/2 pi. And in the middle, I have my critical number of 8 over. And I guess I could make this nicer. I could multiply top and bottom by 4, which would end up being 32 over 4 plus pi. I don't know if that's any nicer, but that does get rid of that complex fraction. You guys haven't seen any mistakes yet, right? Because if you had, you would tell me. We're okay? Okay, I'm seeing a lot of head nods and a lot of nothings, but at least they're not shakings of no. If I plug in like a 1-ish, I don't know, 32 over 7, yeah, 1-ish works. To my derivative, where is my derivative? Where'd it go? Okay, if I plug in 1, 8 minus 1 is 7-ish, minus 3/4-ish, that's still a positive. What am I trying to do? You guys help me out. You had a question on it. You're trying to max? Sweet, I have a max. And they're asking for the dimensions. So my dimensions are going to be 32 over 4 plus pi inches, feet. By, how do I find the y? You guys know what to do. Go back to your clue. Well, 8 minus 32 over 4 plus pi. I'm factoring out the x because it's messy. And then I'll have left 1/2 plus 1/4 pi. Sure, why not? Dun, 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 dun. 32 over 4 plus pi look like what it should be. Okay, everybody stand up, give a high five to someone in your group before we look at your next question, which was 41. My question to you is the following. Did it follow our pattern of max-min problems? Yeah, it totally, completely, absolutely did. Tell me what you got scared of. I know the picture is not up there, but tell me what you got scared of. What was messy? Oh, like the derivative was messy. That's true. Solving for the critical number was messy. Anybody get scared by the semicircle rectangle? But is it scary if you just think of perimeter of a circle as what? Circumference, 2 pi r. Area of a circle is what? Pi r squared. Perimeter of a rectangle, add all the sides. Maybe one of the sides isn't included. Area of a rectangle, length times width. Okay, some basic things that we just need to not be scared of. They're not scary. They don't have to be as scary, at least, as you guys made them. Okay, 41. Calc BCers would really love this one. You guys won't. Logistic growth, I've never seen it on an AP problem. Calc. Okay. Sure, it's the one potential swoop. But all real life doesn't just keep on going forever, so some of it levels out to some sort of limiting constant, especially when you have something like animals on land that are populating. But then don't you have predators or hunters or food supply? Does that make sense? So growing, okay, not anymore. That's why you hear about things like sustainable, like the environment, the sustainable environment for like animal herds, etc. 50 elk, that's why a shepherd would have to take his sheep, because otherwise the sheep would just stay in one spot and be like, must eat, must eat, must eat. There's nothing here, starve. Sheep, dumb. Hey, like us. Must have, must have, must have, not getting anything out of it. Do we look to our shepherd to lead us on? Anyway, game preserve. It is estimated that their population will increase according to whatever. T, years, rate. Oh. Huh. This doesn't look very optimization-y, does it? Okay, well, what's it asking? This is the objective. Rate is the population increasing. Can we just translate this? Rate. Is that P? No, that's how many elk. Rate. Sounds a lot like elk per year sort of thing to me. How do I get an elk per year? I need a derivative and I need to plug into. Oh. So I need P prime of T such that T equals 2? Yep. So I need P prime of T? Yep. So I take a derivative of? Yep. Is going to rewrite them or are you going to quotient rule them? What are you going to do? It's up to you. Rewrite or quotient rule? Quotient rule, okay. So, bottom. D top. Well, that was 0. Forget that. Minus top. D bottom. The derivative of 1, 0. And the derivative of 4e to the u. 4e to the u times. Why am I just going to do negative 1/3 like that's super easy? Because I could 1/3 t, negative 1/3 t, whose derivative is negative 1/3. You could quotient rule if you want. Just be careful, you'll make more mistakes. Or you'll make mistakes more commonly. Over others. 4 times 250 is 2,000, right? Negative times a negative is a positive, and 2,000 divided by 3? Ugh. It's a bad problem. Oh well. 2,000 e to the negative t over 3. I'm going to move the 3 down here because I don't like him. He's messing everything up. Move the 3 down, negative, negative, positive. That's 2,000. There we go. We need to plug in what? Do I have full confidence you guys should be able to plug into? And plug it in your calculator? And give me a unit, elks. Just kidding, elks is not a word. Elk is the plural of elk, like sheep and sheep. Anyway, so elk per year, right? How fast the population is growing after 2 years? After how many years will the population be increasing? Oh, ho, ho, ho. Huh. What does increasing always point to? Which derivative? Population increasing, population increasing. What is that? First derivative, p prime. Most rapidly. Ooh, isn't that a max? Maybe it is an optimization problem after all. Most rapidly, max rate. Max rate? Who am I supposed to be finding the max of? Ooh! How am I going to find the max of p prime? P double prime, if you were doing it by hand. But guess what, kiddos? This is a calculator problem. Could you use your calculator to find this problem? Yeah. Graph what? Him? Actually, no. You could use that really cool n-derive feature and not have done any of this by hand. Oh, that's awkward. You could have done n-derive where you do dx, I suppose, of your p of x such that x equals, isn't that something in your calculator? Pause. Who has a calculator? One person per group. Hopefully, grab it out and find me the derivative function. Oh my goodness, you guys should know how to do this. $250 times 4? Is that what you mean? 0, 0, 2. Oh, sorry, 1,000, right? Not 2,000? Yeah. Some of you saw, you guys, killing me, Smalls. I just rounded up to the next, and I thought I was rounding to 20. I was rounding to 10. Thanks. It's 800 plus 200, so 1,000. Thanks, thanks, thanks. But either way, did you find the derivative? Where is it? No one has one. You guys only have one. You guys only have one. You have, oh. Man, first year. There's not at least like 5 people that bring their calculator every day to class. Someone in a group nearby. So Patricia, show up. Thomas, show back. Or AJ, show back. Either one. Where's the derivative button? Yeah, there's this shortcut where you use alpha and y equals and go over, and there's a derivative. Or there's second trace, right? There's either second trace, go down to n-derive, or there's alpha. What was it? Alpha window? Alpha? Oh, just alpha y equals? Okay. Did we see it? And you can type in and it can find the derivative for you. So the calculator problem in the AP, you can actually just do that? Because there are non-calculator problems where you have to find the derivative. But it's not this hard. Anyway, come back. Come back. If you find the derivative by, wait. If we can use a calculator, we don't even have to find p prime. Sweet. What if we graph that guy? What are we looking for? But can we not derive? Can we graph this guy and find? What can we find on a graph? We can find a 0, a max, a min. What window am I talking about? Go to your y equals and go to the trace. Go to that calc menu where everything cool is. Not trace, sorry. Go to your graph and go to second trace. What are all the options in there? You don't even have to type in the function. Just go to graph, go to y equals, and go to second trace. What are all the options? Start at the top. 0? Value. Value, then 0, then keep going, AJ. Then? The little integral, yeah, summation or summa. Oh, we're just going to find the max, right? The max of, no. What's the max of p prime, where p prime changes from increasing to decreasing? What would that actually be on this graph? A change of signs of the derivative is the same thing as, wait, we were just talking about this. What's going on if p prime is increasing? What do we know? Louder. We know concavity. If P prime is increasing, P is concave up. If P prime is decreasing, P is concave down. So the max of P prime will be when P prime goes from increasing to decreasing, which is when P goes from concave up to concave down, because that's when P double prime goes from positive to negative. Do you remember the concavity test? How all three of these had meanings from the sign of the second derivative? Oh, no big deal. I can just graph him and look for his point of inflection. Did the second trace menu have a point of an inflection option? It had a value, a 0, a max, a min, a derivative, an integral. No point of inflection? Can you use your calculator to find a derivative? Yes. Can you use a calculator to find a point of inflection? No. So here's the struggle. What would you have needed to do? Can your calculator find a max? Yes. You would have needed to derive this function to plug in for the max. You wouldn't have needed it here. You could have plugged into your calculator and made sure you were right, even if your derivative was wrong. If I were you, I would have just plugged in, for instance, for A, just done this. For B, find your derivative so you can graph your derivative so you can find the max, because your calculator can do max. You don't have to. Remember, was it AJ a second ago? I was like, how are you going to do the max of this guy? And someone said, second derivative. Did any of you guys, like, fear was struck in your heart thinking of taking that derivative again? You don't have to do that with your calculator. You have to think of the concept. Wait a minute. If I just need his max, why don't I just graph him? I found him and find the max. That's a good strategy as opposed to, oh, his critical numbers take his derivative? No. If on the AP you find yourself being like it's getting worse and worse and worse and it's going to be awful and horrible, you've probably done something wrong because they don't want you to spend 30 minutes on a multiple choice question. Does that make sense? Or even on one part of an FRQ. Anyway, how would we finish this problem? I think Thomas has been doing it. You would put this derivative into your calculator. You would look for t greater than 0. Don't look negative. That's a bad idea. There's no negative time on this one. Look from t greater than or equal to 0 for a maximum of the graph. Find it with your calculator, and that x value will be your t value for when it happens. And here's the cool thing. It's going to be the same thing or at the same time as when p equals 125. Because with logistic growth, it will be growing the fastest right when the population gets halfway to the limiting constant, but that's something from BC. We memorize it. It's an Endeavor card. It's this whole shebang. Kiddos, what's the one problem we haven't talked about? That one that we skipped, right? Did we spend some time today, though, on homework questions? What do you think I think about this problem, about its importance? Not very important. I had you skip it in homework. We didn't do any examples on it. Now, do we need to talk about it? Yes. Are we going to today? No. Let's go talk about a tangent line. Why? Because tangent lines are easier, faster, not near so much work, translation, deriving skills, etc. are necessary, and then tomorrow we should have time to finally talk about number 13. So is it okay that you haven't done it yet? Yes. You shouldn't have done it yet. Number 13 we'll put at the very, 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 very end of that homework. I'm not checking it on Google Classroom, etc. Okay, we talked about yesterday, if I were to take away the curve, baby tangents are really, really close to a graph for a very, very short amount of time. But they are very, very close to a graph for a very short amount. Well, actually, some of these tangent lines will be close for longer, and some will be, well, they'll diverge very quickly. Two rows diverged in it anyway. So some tangent lines are going to go really far away really quickly, and some are going to stay pretty close for a long time, but we don't know the difference. So we can't use a tangent line, or we shouldn't use a tangent line too far away, or else it's going to be pretty far off. Meaning, if I was to find, for instance, let's just go ahead and put a little x-axis, y-axis, why not? If I was to find, for like a point A, if I was to find L of A, meaning I would find the tangent line and I would plug in A. Would I get a y value? Yeah. Y equals this line, y equals mx plus b. I could plug in A and I could get a y value. No big dealio. The math would be pretty easy. It's a multiplication and then it's an addition. That's it. Could I plug A into F? Who's F? Let's just pretend that it can actually fit on here. How close is L of A's y to F of A's y? Would this be a very good approximation? But what if I was to plug in B? What would L of B be? Right there, on the line. What would F of B be? Right there, on the function. How good's that approximation? Imagine B was even closer. Imagine B was even closer. Imagine B was even... You want to see something cool? I have a question for you before we go ahead and get back to our notes. I have my whiteboard. I'm going to do a different problem than the one I did yesterday with period 6. Totally blank. Do you guys see any calculator, phone, anything? No. I want you guys to ponder in your heads, or even with a pencil, pen, and paper. No calculators, no technology, no Google Glass. Just kidding. Has those. The cubed root of is the cubed root of 122. Pencil, paper, brain. That's it. That's all you can use. With as many decimals as possible. How's it going? Yeah? 4 point something. Good logic. But how do you get decimal accuracy? Oh, my bad. That makes way more sense. My derivative was off. You don't. So you had to somehow write it with an x first.
What would it be 4 when 4 squared is 60 and 60? Yeah, 5 squared is...
Who has a calculator? All three of you. Patricia, go.
Whoa.
What is 4 and 24 25ths? Nope.
No.
Ooh, can you get it in a decimal? You can go 4 and 24 25ths? Do 4 plus 24 25ths. Maybe the operations were funny. And then go to decimal. 9. Give me a few more. 9. Oh, that's it? Oh, it's perfect? Okay, cool. Can you get the cubed root of 22? Or of 122? So you can do 122 to the 1/3, or you can use the cubed root. How'd I do? How'd I do? What do you see in my work? Thomas, hold it up right here. So it's facing you, you can see it, but so can they. What do you see in my work? I made an equation. What was my equation that I made? No. What was the equation I made? Cubed root of x. Why did I make cubed root of x? Because what was going on to the 122? Cubed root of who? 122. Do I know the cubed root of 122? No. I know 125, and it's close to 122. If I were to ask you the cubed root of 117, my approximation would be farther off. If I were to ask you the cubed root of 80, my approximation would be farther off. Don't worry, we still have 5 minutes. What do you see right here?
Oh.
It's a tangent line at what point? 122? Heck no, techno, I don't know him. 125 was my point of tangency. I took my derivative, I made my tangent line. Oh, sorry, Thomas, one more second. Where did I put the 122?
Oh.
And then math was how to do, like the cubed root of 125 was 5, and 5 squared is 25, and times 2 is... Did I write that wrong? Sorry, my derivative is 1/3. I did it right. I just didn't write it. Bring down the 1/3. Stop. Okay, I can do 3 over... look. So what do we do? Exactly what I told you yesterday. What do? We make a tangent line. We solve for the y of the tangent line. We call him L of x. He's our linearization. He's our tangent line that we're about to use. And we can approximate an f of with an L of by plugging in. So over here, this one actually is even nicer than mine. Mine, I didn't tell you anything, but go ahead and just play with the cubed root of 122. Why'd I do that? Because it was close to 125, and I'm like, I'm going to do all right on that one. Does it help you with every approximation ever? No, but it helps you with the ones right around the perfect ones. This one says, hey, guess what? Your function is. Oh, they told me the function. That's nice. This is my point of tangency. X is 1. Y? I know 1. The square root of 1 is what? Yeah. So I'm going to use the tangent point, 1 and f of 1, otherwise known as 1, 1. What am I going to do? Make a tangent line. How? I know how to make a tangent line. Y minus y1, 1, equals f prime. Uh-oh. X minus x1, 1. What's my derivative of square root of x? It's x to the 1/2. Bring down the 1/2 and make it a negative 1/2. Now pause. Some of you need a highlighter right now. I'm not going to draw or write an x. X doesn't belong. Who belongs? 1. We need to put in the 1. Yeah? Careful. My highlighting people. X does not go in here. A 1 does. Because it's f prime of c, not f prime of x. Be careful, be careful, be careful. One of the most common mistakes with tangent lines. Plug in the 1. Now what do we get? Oh, y is equal to 1/2 x minus 1 plus 1, right? And who is this going to be? Is that going to be used to approximate? F of x. So my L of x can be used to approximate square root of x. For what? I don't know. How about 1.1? What's the square root of 1.1? 1-ish? Better. What's the square root of 1.1? Well, square root of 1.1 is the same thing as f of 1.1, which I can approximate with L of 1.1, which means there's an approximate between the f and the L, but over here all I have to do is plug in. 1/2 times 1.1 minus 1 plus 1. Can we do that math? Yes, because 1.1 minus 1 is 0.1. 0.1 times 1/2 is 0.05, and 0.05 plus 1 is 1.05. So what do I think the square root of 1.1 is approximately? Patricia, calculator, square root of 1.1. Thank you, ma'am. Dun 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 dun. Should have done. Anyway, we got it? It's all Maggie Corey. What we really do on mission trips. Anyway, so, oh no! This section. The idea of differentials. Wait, differentials. Here's the cool thing with the idea of differentials. Delta y says, okay, how do we go from one y to another y? dy says, how do we go from one y to another y? Sometimes. But how do we get dy? Guess what? Pause. So in homework, when it says solve for dy or get dy or solve for the differential, guess what it means? Take the derivative and times dx. Really? Yeah. Take the derivative and times dx. Can you use that sometimes to approximate delta y? Yeah. I want you guys to see how far you can get in homework. I know it's at least through the first 3 sections and maybe even farther. The word problems might be a little tricky, but I'm still going to have the Google Classroom due tomorrow. Get through everything up to the word problems and maybe just try one word problem. Sound good? Cool. How do you get dy? Derivative? Put a dx at the end. Ha-ha! Bye, guys. See you later, alligators. Play with your tangent lines. Wow, some cool Algebra 2 kid who actually cares about math with some sort of random root today. Rebecca, here you go, kiddo. Rubber band trouble? Sorry, kid. Been there, done that. It was rough.